All right, let's get started. Hey guys, what's up? You guys are all alive. Okay, that's good. Well, at least most of you. I don't know. There are like 2 people missing, I think. And yeah, hopefully you're all doing well. Welcome to another class. We are on the last leg of classes. And so I just want to make sure that I'm checking in, making sure everyone has a pulse, making sure everyone's following along and all that good stuff. And yeah, so we don't have much time. I've learned by doing a couple of these that the time goes by a lot quicker than expected. So I'm pretty much going to want to get started right away. We're going to jump right in. So I would like to share this OneNote file, and hopefully you guys can all see that. Okay, so this is what we're going to cover today, polar coordinates, which is section 10.3 of the textbook. We're not going to go into this as deeply as the textbook does. We're going to just do some kind of like an intro of what these guys are. And yeah, so without further ado, let's actually just jump into it. And you guys can just hop in whenever you have a question. Also, I've been in and out of Zoom meetings all day, crazy time. And I have been having some technical issues earlier. And so what I have found is sometimes sharing my video while showing this can sometimes cause an issue. So while I'm lecturing, I'm going to actually turn my video off. But I'm here and you can just listen to the soothing sounds of my voice talking about math. Okay, all right. So we are going to cover polar coordinates right now. And basically what this is, it's actually a new way of looking at the world. And it's actually going to be very, very, very important in semesters to come, whatever that might look like. So I'm pretty sure that during the summer, we will still be online. I have no idea about the fall though. So for any of you who are going to take Calc 3, which is Multi 1, this is going to be super important and you are going to want to know about this. Now, there are some things that can be left out here, and in the interest of time, I will leave those out, but knowing the basics about polar coordinates is going to be very, very important. Now, what are polar coordinates? Well, a coordinate system is a way of locating things in a space that we care about. And what we are used to doing is what's called a rectangular coordinate system. So when we've been doing the XY plane, how we've been looking at the XY plane this whole time, how we go about sketching curves and how we locate coordinates in the XY plane. This was using what's called the rectangular coordinate system. And no surprise, it's called the rectangular coordinate system because it uses coordinates. So for example, here is the XY plane. And let's say we wanted to locate these points. How would we actually go about doing that? Well, to locate the point 1, 5, what is it that we did? Well, we understand that the first coordinate was the x coordinate, the second coordinate was the y coordinate. We move 1 on the x coordinate, and we go to 5 on the y coordinate. And moving a line from the y value parallel to the x-axis and from the x value parallel to the y-axis, where these 2 lines meet, notice that we form a rectangle here, where the origin is the corner of one of those rectangles, and the point opposite the origin is the location of the point. So that is the location of 1, 5. Similarly, I could find 3, 1. That leads to this other rectangle where the corner opposite the origin is going to be the location 3, 1. Now, when we have negative coordinates, of course, you all know what this means, but I just, for emphasis sake, negatives really just means you move in the other direction on the x-axis, right? So instead of moving to the right, a -2 in the x tells us to move to the left. So that's where -2 would be. And on the y, positive is the up direction, negative means we move down. So we would move down to -3. And again, a rectangle is going to get it done. The corner opposite the origin is going to be the location of the point. So this is the location -2, -3, right? So this is the XY plane, the Cartesian pair of axes, and this is how we locate points in the plane. This is using the rectangular coordinate system. Okay, so now we actually want a different way to locate points in the plane, and we don't want to actually use rectangles. We actually want to now use a whole different object. Namely, we want to use circles, okay? So instead of doing something where we look at X and Y as two coordinates that we connect with a rectangle, we are going to imagine that points in the plane, how I want to locate a point is, let's move this in a little bit more here, is I'm going to imagine that that point is lying on some circle centered at the origin, calling that radius r, and the angle that is made by connecting the origin to that point, this is an angle theta. And so this coordinate would be the r theta coordinate, right? So now instead of rectangles, we use a distance from the origin, which is what we call r, and then angle made with positive x-axis, which we will call theta, right? And essentially what this is, it's kind of thinking of the entire XY plane as just a bunch of concentric circles. And any coordinate in the XY plane, we can think of it as lying on the circumference of some circle. The radius of this circle will be the r coordinate, and the angle, if I connect the origin to the point, the angle made with the positive x-axis is going to be the theta coordinate, right? So we're using a distance and an angle to describe it instead of two distances, right? And that's it. That's basically what polar coordinates is. It's just a way of looking at coordinates in the plane in this way. That's all it is. Now, this will obviously have some consequences. And any system that we use this kind of way to locate, that's called a polar coordinate system. And the coordinate r comma theta is called a polar coordinate. So for example, let's say I wanted to locate the point r comma theta equals pi over 4. Well, what would that look like? Well, that means I want a point that is at an angle of pi over 4 from the positive x-axis, and from the origin, it extends to a distance of length 1. So this is going to be the point 1 comma pi over 4. And this length here is 1. Okay, so everyone's with me so far, I think? Yeah. Okay, so hopefully now you would recognize certain things would actually be the case here. One thing that you can notice is that in polar coordinates, our coordinates will not have a unique representation, right? So that's one difference between the rectangular coordinate system and the polar coordinate system. In the rectangular coordinate system, when you say 1 comma 5, there is literally only one coordinate. There's one location in all the universe in the XY plane that has that position. 1 comma 5 is the only guy. Once I change the 1 or the 5, it is no longer this location. In polar coordinates, this is not true. You would notice that in every time I were to go around, let's talk about this. So every time I would go around the axes by a magnitude of 2 pi, I would actually hit the same thing. So I can look at this here is pi over 4, which corresponds to this angle. But I could also go all the way around and come back here and hit the same line. And so this is actually the same as, say, 1 comma pi over 4 plus 2 pi, so which is 9 pi over 4. These two coordinates, r comma theta, are the same location, right? Even though they have a different representation. And of course, I can keep doing this. So that's what this is talking about here. I mentioned here. Every time I add a multiple of 2 pi to a coordinate, I would actually get the same location as long as I don't change my r. There's another thing that I want you to realize here is that we do have a notion of negative distance with this system as well. What does it mean to be a negative distance? So when I say r is -1, this is another situation that you're going to need to know. What does that mean? Okay. So again, the angle is pi over 4, so we kind of know what that means. I don't know, should I put this in a different color? So I'm going to move at an angle of pi over 4. Now, in magnitude, if I look at the distance 1, that would be over here. This is 1 comma pi over 4. Now, what does -1 mean? Negative means, oh, negative, just like in the rectangular coordinate system, means reverse the direction. So just as how a negative x means we move to the left as opposed to the right, and a negative y means we move down as opposed to left. So too, in the polar coordinate system, instead of moving towards the 1, towards the angle pi over 4, I want to move away from the angle. So it literally does a reflection about the origin, right? So just as how with x, +1, to get the -1, you take a reflection around the origin, and positive y values, you take a reflection around the origin. Similar to here, along this angle, you take a reflection around the origin. So this is the point down here of -1 comma pi over 4. So that also actually tells you that even the r value in a polar coordinate system can be changed. So I can actually make a negative value. So for example, if I were to, again, let's keep this pi over 4 as the same guy. So here, I move pi over 4 along a distance 1, and that locates the point 1 comma pi over 4. Now, of course, I could go all the way around adding 2 pi, and that also gives me pi over 4. So this is the same as the coordinate 1 comma 9 pi over 4. But now, taking our cues from the negative, what I could have also done was move at an angle that's exactly opposite to this one. Namely, that would be the angle 5 pi over 4. And then make the distance negative, so I flip opposite to that. And that is, these coordinates are, and there's an infinite number of ways to express this coordinate in polar coordinates. There are ways that you can express it where the r value stays positive, and it's just going to be this guy plus multiples of 2 pi. Or if the r coordinate is negative, it's going to be this guy plus multiples of 2 pi here. Or multiples of pi if I want to take away from the pi over 4. So that's polar coordinates. That's how we locate things. Any questions so far? Questions, comments, concerns? Chime in at any time. Are we all good? Are you guys actually hearing me?
Yeah.
Yes.
Okay, so so you guys are there. Okay, do we have any questions on what we've been saying so far?
This might be a kind of a dumb question, but does it matter what you find first, or like, if you find r first, or if you find theta first? Like, say if you have like -1 comma 5 pi over 4, does it matter which one you find first? Like, will it affect where you land or no?
No. So if you go by finding the r first, essentially, if you look at say -1 comma 5 pi over 4, so someone who would locate the r first is the person that would have a circle of radius 1 as their picture.
Mhm.
And then when they locate the angle 5 pi over 4, that's when they get this line showing up. And knowing that it's negative means that it would flip over here. So you would get that point.
Okay.
So this is if you consider focusing on the r first, you actually get the circle. Conversely, if you focus on say -1 5 pi over 4, focus on the angle first, the first thing that's going to show up in your mind is going to be this line here emanating at an angle of 5 pi over 4. And then you're going to say, okay, I want a distance of -1 along that angle, but -1 means I flip opposite. So here, so I'd still locate the same point. So yeah, the order in which you locate them here doesn't actually matter.
Okay.
Okay, all right. Now, moving along, the fact that we have this idea of, say, an angle and a distance kind of course, tells you that trig is going to be very important here. What we could do is we can actually complete a right triangle from this picture. Now, obviously now with SOHCAHTOA, we can figure out a few relationships here, right? So if this height here is of course the y, and this length here is of course the x coordinate. And of course we know that sine of theta is equal to opposite over hypotenuse. Therefore, I can solve for the y to get r sine theta. Cosine theta is adjacent over hypotenuse. Therefore, I can solve for the x to get r cosine theta. So these equations will take effect automatically once I'm working in this coordinate system. Also, as should be clear, because this thing represents a circle here, this is a circle of radius r. Basically, what we have here is its equation would be x squared plus y squared equals r squared. And so this equation would take effect right away. And of course, if you want to actually solve for the theta, tangent of theta is opposite over adjacent. So tangent of theta is y over x. And so your theta can be thought of as a tangent inverse of y over x. And so these equations immediately become apparent from trigonometry, and they're actually pretty useful. In fact, the first pair of equations, which both of these should be asterisked, you should know these sets of equations by heart. The first set of equations helps you to go from an r theta situation to an xy situation. So we might have to convert between coordinate systems every now and then. That's going to be important. Sometimes you're going to be given something in rectangular coordinate system and you want to convert it to polar coordinate system. And in multi-2, you'll realize that this is actually very important. It really make a lot of, hold on. My headphone was also connected to my cell phone. I want to disconnect it so I don't get alerts. Okay, so these coordinates are actually very useful in converting from polar coordinates to rectangular coordinates, and these guys are useful in converting from rectangular coordinates to polar coordinates. So let's actually do some examples of these conversions. Here I gave you some points, r thetas. If r theta is 2 comma pi and r theta is radical 3 pi over 6, convert this to rectangular coordinates. Okay, so let's actually see some of those in action. So I have a theta, r theta. In the r theta universe, I am at the location 2 comma pi. How do I know what this looks like in the xy universe? Well, we know, now we know, your x would be r cosine theta. So in this case, it's going to be 2 cosine pi. What is the cosine of pi? This is where you guys jump in.
0.
No.
-1.
Sorry, yeah,
-1. So cosine pi is -1. Y would be r sine theta. That's 2 sine of pi, sine of pi.
0.
Now that's 0. Okay, so that was the other one. So this is actually the point. The xy coordinate here is actually -2 comma 0. And that should probably make a lot of sense to you. If you are looking in the polar coordinates version, this is an angle of pi, meaning you go like here, that's your pi, and then you go a distance of 2 units away from the origin. That brings you here. Now, clearly, as you can see in the xy coordinate system, this distance 2 here would of course be -2. And in the xy coordinate system, this is -2 comma 0. Okay, so that is, so 2 comma pi in the polar universe is equivalent to -2 comma 0 in the xy universe. Similarly, let's move this one down. Radical 3 pi over 6. So obviously you are going to have to remember your trig here. So if r theta is square root of 3 comma pi over 6, this means that the x coordinate is going to be r cosine theta. This is going to be radical 3 cosine pi over 6. Cosine pi over 6 is radical 3 over 2. Y is going to be r sine theta. So that's going to be radical 3 sine of pi over 6. Sine of pi over 6 is a half. So this means that your x comma y would be 3 over 2 comma radical 3 over 2. And does that actually make sense? Well, if I look at this polar coordinate, I'm at an angle of pi over 6 and at a distance of radical 3. Yeah, so the x and y coordinates are positive, so this actually makes a lot of sense. And with trig, you can figure out that the x value would be this and the y value will be that. So that actually makes a lot of sense. It's in the right quadrant, so we're good. Moving on, we can go the other way. We'll talk about these later. We can go the other way, and given points 1 comma 1 and 0 comma 2, normally if you don't mention it, it's going to be assumed that it's xy. Convert these to polar coordinates. So those are going to be very similar. So I'm going to have, so if my xy is 1 comma 1, then I know that r squared is going to be equal to x squared plus y squared. This means that your r squared is going to be 2. This means your r is plus or minus radical 2. Now, whether to take the plus or minus, we can actually take either. We just need to make sure that the angle corresponds to the value of the r that we want. So don't worry about should I take the plus. You can take the plus just because, but it's not completely necessary. Now, if you look at the y, we also know that the theta is going to be the tangent inverse of y over x. This means that your theta is tangent inverse of 1, which means your theta is going to be pi over 4, and potentially some reference angle version. It depends on what sign we take, some non-reference angle version. Now, to make sure that your angles and distances coincide, what you could do is you could actually just draw a picture. We know that 1 comma 1 would look like this. So we are in the first quadrant, which means I can just take an angle of pi over 4 and move a distance of radical 2. And so I can think of this as r theta is radical 2 comma pi over 4. Another option, I mean, that's good enough, but another option would be I know that the angle is, say, pi over 4, and I know I want to go here, but another option would be to go to the angle 5 pi over 4, and then just make the r value negative. So this would be minus radical 2 comma 5 pi over 4. It will actually give us the same location. There's an infinite number of ways you can express the polar coordinate version of the coordinate. So yeah. Moving these down. The other one, 0 comma 2. So our r squared is going to be x squared plus y squared. So this would mean that your r, yes, Syed?
Oh, sorry to interrupt you. I was just a bit curious.
The last one?
No, I was asking. The recitation teacher, he's hosting his recitation at 2 p.m., so it kind of conflicts.
Oh, he says it's due at 2? You guys can go after.
All right.
Yeah, I'll tell him. Okay, so we have our squared here. Where am I? I lost my train of thought. Okay, so this was 0 squared plus 2 squared. So this means your r is, well, plus or minus 2. How would you find the theta here?
Do tan inverse of y over x.
Okay, but what would that give you here?
That'll be undefined, right?
That would be undefined. So here's something that you want to notice here. Here, y over x, undefined. How do you think of dealing with that?
Well, now we have an r, right? We have an
Yeah.
r value, so we can use like r is equal to like one of the formulas from before. Like r is equal to.
So you can use like x equals r cosine theta or something like that?
Yeah, exactly.
Right, so now your x, so the tangent version won't work. Tangent theta won't work. Now, the fact that the tangent theta won't work would also indicate something to you, but let's just run with this, for example. The x, we know that the x is 0. The r is, well, it's plus or minus 2. And you can just take it to be 2 for now. Cosine theta. So in other words, this means that cosine theta is equal to 0, which is why the tangent is undefined, because tangent is sine over cosine. But what happens there? That means your theta is going to be some odd multiple of pi over 2, which is something you can tell from the tangent where the tangent doesn't work. This guy does not work at odd multiples of pi over 2. So the fact that the tangent itself is undefined actually indicates to you that the angles would look like this. And you might as well just take the positive pi over 2. That actually works nicely with this guy. Another thing you could have done is just to realize, so here, take theta equals pi over 2. And this would make a lot of sense with the picture. If we look at 0 comma 2, that guy shows up here. So obviously that here, that's the angle pi over 2 and moving a distance 2 units up. So that actually makes a lot of sense. r theta is equal to, I can just say go pi over 2 and move a distance of 2 units. And that'll be your answer here. Now, one thing that's going to be very important coming in the future. So that's polar coordinates. That's how they work. These equations come in handy if you want to convert between coordinate systems. But one of the most important things that you'll need to know about polar coordinates is how to express regions in polar coordinates, or at least look at a description of a region and be able to describe that region in polar coordinates, know what it looks like. Sketching polar curves it's pretty cool, but we're not going to do that. It's one of those luxury topics. Do it if we have time. So, for example, describe in polar coordinates the region bounded by the quarter circle in the first quadrant, which is the circle of radius 3, and the positive axes. So we are looking at this region here. Okay. Now, I could describe that in rectangular coordinates. It's bounded by the curve, the square root of 9 minus x squared, and x is greater than or equal to 0, y is greater than. So in rectangular coordinates, maybe that's nice for the comparison. In rectangular coordinates, how could I describe this region? In rectangular coordinates, I would describe this something like, well, my y is less than or equal to the square root of 9 minus x squared. My x, I want it to be greater than or equal to 0, and my y should also be greater than or equal to 0. Right? These three inequalities would describe this region. Any guesses as to how the region will be described in polar coordinates? Tell me about how r and theta would have to behave. Any guesses here?
Would R be 3?
Well, R3 is this line here, but I want the entire region. So you do want an inequality.
Would theta be equal to 90 degrees?
Well, R is less than 3. Also, theta equals 90 is literally only this angle here. You want all this region. So someone mentioned R is less than 3. Almost. We definitely want it to be less than or equal to 3. But of course, greater than or equal to 0. This is all distances from the origin moving all the way out, right? So 3 is just this point out here, way out here. 0 is when I'm right up against the origin. I want those numbers and everyone in between, right? If I only wanted the outer circle, if I look at r equals 3, well, this is literally only the edge. Once I say r is less than or equal to 3, now I get the edge plus all the closer stuff, right? So in the second quadrant. Okay, so we need an inequality here when you're describing a region. Similarly now, the theta, yeah, pi over 2 is this part here, but I also want everything ranging from 0. So these inequalities would be how I describe it. Now I want you to appreciate why this might be useful, as you are going to see in your future classes, of course. Look at the inequalities that describe this in the rectangular system, and look at the inequalities that describe it in the polar system. This guy requires a radical, very complicated looking function. If you have here, you'd have to solve for the plus or minus of the radical, if you could even solve the equation to begin with. In this case, we lucked out. Then you have to make some decision as to would I take the positive or the negative, or maybe it's very hard to even solve for this equation, right? So this is a very nice problem. This could get a lot uglier in rectangular coordinates. However, look at the polar coordinate situation. These are constants. These are numbers. Literally in the polar coordinate universe, if I were to plot this as theta versus r, we have a rectangle here. The theta goes between 0 and pi over 2, and the r goes between 0 and 3. In the polar universe, we are looking at a rectangle. In the XY universe, we're looking at the part of a circle. Now, for various reasons, we like rectangles. You might, for example, think about the fact that when we were defining integrals using Riemann sums in Calculus 1, we did that whole thing with rectangles. Rectangles were nicer for us to deal with than circles. So if we're in a situation where we're a circle, in a strange way, the polar coordinate system can have us treat it almost as if it's a rectangle, albeit in a different universe. That you don't have to worry too much about, but I just want to give you the, show you the fact that this region is very complicated, or relatively complicated, if I describe it in rectangular coordinates versus describing it in polar coordinates. Instead of having to deal with all these radical functions over here, I now only have to worry about constants. And that is going to make your life so much easier in certain situations in multi 1. It's not going to be funny, and that's going to continue multi 2 and forever, as long as you're using calculus from that point on. This conversion will help you whenever you're looking at a circular region. So another important kind of circular region is something called, let's move this guy down. There is something called an annulus. Okay. And I just described one using these units. So here I use 2 of these inequalities. So in other words, this is basically me saying, and I didn't put any quadrant restrictions here. So if I were to graph this, and I wanted to graph, say, x squared plus y squared is less than or equal to 9. Okay, so that's going to be this guy. That is a circle of radius 3. And let's say I shaded all those parts green. So if it's less than or equal to 9, that means it's everything up to 9. Obviously, x squared plus y squared is going to be larger than 0. So it's everything from a distance of 0, all point coordinates from 0, 0, extending to the point where the x squared plus y squared is less than or equal to 9. The other guy we can get is, say, the x squared plus y squared is greater than or equal to 1. So here's the 1. And that's that guy. Now I want greater than or equal to 1, which means I want the guys outside of that circle. So it's all of these guys over here. So this is what gives you an object that we call an annulus, which is basically 2 concentric circles, kind of like a washer. And you can describe it in rectangular coordinates with these 2 complicated equations, where if I wanted to deal with functions, I had to solve for the y, I'd get radicals, I'd have to worry about pluses and minuses, I have to do all this stuff. However, in polar coordinates, This is just r goes between 1 and 3. And my theta goes between 0 and 2 pi. Right? These two complicated equations, inequalities, become two very simple inequalities. Right? Look at this thing. I'm keep moving these guys. But look at this guy here. Describing polar coordinates the region where y is greater than or equal to x, x is greater than y is greater than or equal to minus x, and this is true. So I can go through, okay, look at this, that. I would think of y equals x. So y equals x. That's basically this guy. And I want to be bigger than that. So I'm looking at things moving in that direction. And I have y is greater than or equal to minus x. Well, y equals minus x is that guy. And again, I want things on top of that because they're greater than or equal to that. And then, of course, I have this part here, which, as we know, is a circle of radius 1. And I want to be inside of that. So pretty much I want the region that satisfies all of these at the same time. So I want to be above this, I want to be above that, and I want to be below this. That gives you this region over here. It's like a pizza pie, a pizza slice. So here's all the complication I had to go through to describe this situation in rectangular coordinates. What about polar coordinates? Again, simple. R goes from 0 to 1. Theta would go from pi over 4 to 5 to 3 pi over 4. Again, that's still just constants. We're looking at things that looks very complicated here, and once they're circular though in the xy plane, it turns out that they look like constant functions in the polar universe. That one is actually, that was easier than the other examples. I think I did these examples out of order. But yeah, this one is just x squared plus y squared less than or equal to 16. That's a circle of radius 4. You want everything in here. Yeah, that's r is between 0 and 4, theta between 0 and 2 pi. Stop. That's actually all I wanted to cover for polar coordinates. I mean, here I mentioned that we'll skip this section. It's kind of optional. It's really cool, but it's not really something you're ever going to see again. So I don't really want to waste time on it, given everything that's going on. I might do an extra lecture, maybe throw it on a bonus or something, but not really going to worry about this stuff. But graphing equations like this, like what would it mean to graph it? Like we know that these circles are actually rectangles in the polar universe, but if I had something that was a trig function in the polar universe, what would it look like in the XY universe? It turns out that it will actually look pretty cool. So for example, if I were to draw this one, let's, graph.tk. This is something I told you guys about before. Can also graph polar stuff. 1 plus, I forgot what it was. Was it 2 cosine 3 theta? Yeah. And look, that's the graph. That's what the picture would look like. This line shouldn't be there. I don't know why that's there. Yeah, so some of these graphs are really cool and they're really fun to do by hand, but I've never seen anyone outside of Calc 2 actually needing to know this. So while it's very interesting, very cool, it's fun to teach, fun to draw these things. Yeah, so imagine what the equation of this would look like in the rectangular coordinate system in x's and y's. It's not even a function. A vertical line will cut this guy 1, 2, 3, 4, 5, 6, 7, 8 times, right? So the formula in x's and y's is obviously going to be very, very complicated. But it's a simple trig function in the polar universe, and it actually gives us a graph like that. But yeah, that's that. Yes, Syed?
I have a question
Yeah.
regarding the like test or examination.
Yes.
I was wondering when the next exam would be, because I remember I talked to you earlier and you said it would be like in the end of the month or something.
Yeah, so our last class, I believe, is Wednesday, if I'm not mistaken. And the test is on Tuesday, and it will be online. So I have to organize with Rolf on this, how to get the timing set up. But I'll try to make it during the regular recitation time.
So how it'll work? It'll be like
It'll be like a paper test would have been. So you guys will have the test. You will do the test on paper, and you will essentially scan the answers and send it back to me. Which you can there are apps on your phone that you can take a picture and
will we be given like a little bit of time to scan it, since I know from our other
classes? Yeah, like at the end. Yeah.
All right. Okay. Thank you. So it's going to be on Tuesday, right?
Yes.
All right.
And I'll send you, I'm still working out the technical details, but I'll let you guys know. But in terms of, other than the scanning part, it's essentially going to feel like a regular test. You're going to write down all your work, and then you're going to send that to me, and I'm going to grade everything and give you partial credit and everything. So it's semi-online. It's online submission, but you do have to take it during the recitation time, and yeah, we'll proctor. I'll see if Rolf or myself.
All right, thank you very much, Professor. I appreciate it.
Yeah, and the test is covering everything up to today, I guess. So everything after the first test. So everything after integration. So everything that we've done with series and polar coordinates. And I'll probably put bonuses on conic sections, which is the next thing I want to talk about. And maybe vectors, which hopefully I want to get to vectors by the end here.
So it's pretty much just going to cover series and polar coordinates for the second exam.
And parametric equations. So remember, we actually covered
that.
Yeah.
Okay.
So series, it's going to be, and I'm going to post a review for it. So series, this means you need to know how to tell whether a series converges absolutely, conditionally, or diverges. You need to be able to construct a Taylor series. You need to be able to use a known Taylor series to figure out the Taylor series of some other function. And you need to be able to apply this to integration, right? So if I give you a very weird function to integrate and a definite integral, know how to do it by doing a series and approximating the answer, and yeah, that kind of thing. And then parametric equations, you should know how to sketch them, know how to take a derivative of one and a derivative of one, find the second derivative, know how to find tangent lines, know how to, yeah, everything we did in the parametric equations lecture. And then polar coordinates, know the basics of how to represent regions and what a polar coordinate is. Yeah.
And then like
it should be, I don't know how you guys felt about series, but sometimes students find it easier than integration. Sometimes they find it harder. It should be easier test, I think.
Definitely a little easier, at least for me.
Yeah.
Do you have any information regarding the final exam? Like when that's going to be, how that's going to be distributed? Anything
It's
like
definitely
that?
online. That I know for sure. In terms of how it will actually be administered, I do not know. If I do not get any further instructions or they leave it up to me, then however I do the second test will be the same protocol for the final.
Okay.
But that's if it's left up to me. So I did send emails again up to yesterday, so I'll wait to hear from them.
Okay. Sounds good. Thank you.
Okay. All right. Apologize to Ralph. I didn't realize that he said it for 2, or I just forgot. There's been so many things going on recently. So many emails back and forth. I don't remember what time I'm supposed to be anywhere. So, just to point out that the email I sent with the link to this, it says Pacific time in it for some reason, but it's of course Eastern time. So we are going to be doing this for the remainder. So for the next week and a half, we'll meet here. And yeah. So without further ado, I will let you guys go. You guys can go check in with Ralph if you guys tried the quiz earlier. And yeah, we will stop there for now. So until then, hope everyone's all well and safe. Ciao.
Thank you.
Sorry, will
Thank you.
will the quiz solutions be posted?
Will the what?
Quiz solutions be posted?
Sure, but you can also talk to Ralph about it. But
Oh,
I'll post those later.
it's because I have a class at 2:30. That's why.
Okay. Well, I probably won't post them today, but at some point I'll let you have them.
All right. Thank you. Have a good day. Thank you.
Okay. All right. Take care, Syed. All right. Bye, everybody.
Thank you.